Now I'm going to start the Introduction to Statistics Take 2. Hopefully not get deleted here. I've opened the set of notes directly from the Canvas page, so this is exactly what's posted for you. So the first thing is that the purpose of statistics is to be able to take information from a sample of people or households or animals or whatever, and then try to learn about everyone from that. Statistics is defined to be the science of collecting, organizing, summarizing, and analyzing information to attempt to draw conclusions. Data is information that has been collected. The population is the entire group of individuals being studied, not the ones that you survey or particularly study, but the whole group. And the sample is the subset of that population that you actually do study. A parameter is a numerical summary of the entire population, which is pretty rare to have. So if you happen to have the average age of all statistics students in Plano ISD, the median salary of all professional basketball players, as opposed to a statistic, which would be regarding a sample, so the average age of statistics students at Academy High School, particularly, or the average salary of the Dallas Mavericks, particularly. And of course, these would be not the same. The average age of statistics students at Academy High School, well, you guys are all third years, and in all of Plano ISD, probably at least half statistics students are seniors. Descriptive statistics is where you're organizing and summarizing data. So it's tables, graphs, things like that. Inferential statistics uses methods that take the result from the sample and then extend it to the population, and then you have to have an error. So if I were to take a survey and find out, say, the average size of television that people have, that wouldn't be the exact average size in the population, but if I did my sample right, it would be close, and I'd be able to say how many inches I'd likely be off. Variables are the characteristics that you're measuring. So we have qualitative and quantitative, which are also, as far as on-ramps is concerned, often referred to instead as categorical and numerical. So qualities, quantities, this one is qualities of the person or animal or house or whatever. And this is quantities, so this is numbers. Within numerical variables, you have either discrete ones or continuous ones. And essentially, if the answer could even theoretically take on any value, then it's continuous. If there are only certain types of values it could take on, then it's discrete. So if it's like the number of cars you have, that can only be 0, 1, 2, 3, 4, so forth like that. So that's discrete. But even if it's, say, that you're talking about how much of a pie you've eaten, and let's say that we're just assuming it's perfectly cut into 8 pieces, then you might have taken an eighth or a fourth or 3/8 or a half, but it's still, I can list out the possibilities. It's not any possibility in the world. If you're thinking about instead like height, well, generally speaking, people only give height in quarters, right? But in reality, a person could be 5, 6, and pi over 4. That is a height that someone could be if they were exact. So anything really that's measured is technically continuous. Within levels of measurement, we have 4. The first 2 are usually categorical or qualitative. The last 2 are numerical. Most numerical values fall in the last 2. So the nominal level, nominal means like naming. You've just named it. That's it. It's just a category. So if you have something where the answer is like a color or um, okay, sorry, I paused recording, so I don't know where I left off. But nominal level is things where it's either a yes or a no, or if it's, what's your favorite type of fruit, things like that. So it's just you would put people in categories only. Ordinal is still usually categorical, but it means that there's an order to it. So if you had, say, freshman, sophomore, junior, senior, those have an order to them. And first place, second place, third place, grades. Of course, we don't have D's, but ABCF. Anything that's in an order like that. Interval means, so by the way, to get to one level, you have to have been all of the preceding levels. So yes, anything could be in some way listed as a nominal level, but if it's interval level, then it's at least interval level. So these are kind of increasing specificity. Intervals are the range of numbers between two numbers, and you can consider the length of an interval. So interval level means subtracting, and the length of an interval is subtracting the two numbers. So the interval level is when subtracting makes sense, basically. So if you say well, a couple of days ago it was 95 degrees, and today it's like, I don't know, 75 degrees. And if I subtract those, it was 20 degrees warmer 2 days ago, or it's 20 degrees cooler today, and that makes sense. So it's at least interval. Pretty much anything numerical, not like first, second, third place, but almost anything that's a number is interval, if it's a quantitative variable. The difference between interval and ratio is that to get a ratio, division has to make sense. A ratio is a fraction. So fractions have to make sense. So if you take something like age, if one person's 40 and one person's 20, then 40 divided by 20 is 2, and indeed the first person was twice as old as the second one. That doesn't make sense in temperatures Fahrenheit. If you say 95 degrees divided by 75 degrees, that results in a number, and that's 19 over 15, but it's not 19 over 15 as hot. Similarly, if you, instead of asking the ages, if you ask the year of birth, so the 40-year-old, I guess, would have been born in 1974, and the 20-year-old in 1994. 1994 divided by 1974 doesn't tell anything about the ages, the relationship between those ages. So dividing doesn't make sense for those. But very few things are actually on the interval level, because most things do make sense to divide. The quick way to tell is consider what the zero means. If the zero means complete absence of whatever you're measuring, then it's ratio. So height, if you say somebody's 0 tall, then there's a complete absence of height. But if it's 0 degrees Fahrenheit, there's not a complete absence of warmth. If you have the year 0 was not the absence of time, it was a year from which we started counting. So that's what makes those interval and not ratio. At some point, I don't know if you'll see this before I do this, but at some point I'm going to add a couple of questions there. So studies versus experiments. You want to determine how varying the amount of an explanatory variable affects the value of the response variable. So an explanatory variable might mean the amount of medication given, and a response variable might be the amount of pain experienced, or the length of recovery time. A designed experiment is when you assign the people in the study to a certain group. So you give people different amounts of medication, or maybe you just give the medication to one group and not the other. And then you see the difference then in the response variable. So you've heard of a placebo. If you give people a medication for pain, then you have to have one group that's called the treatment group that gets the medication and one group called the control group that doesn't. And then you see how they report their pain, because sometimes people, having taken the pill, will believe that they have less pain, and so they'll experience less pain and they'll report less pain. So you want to know if there's a real effect by the medication. An observational study is when you just observe the behavior of the individuals and you do not control anything from the explanatory variables. So something that has to be observational is, say, a study about smoking. So you can't tell people you smoke and you don't, and 3 years from now we'll check your lungs. So you have to let people make the choice themselves in an observational study. In the case of an observational study, you can't really claim causation. If you do a designed experiment and you've designed it very, very well, then your control group and your treatment group should be similar in all ways that you can think of that might affect the outcome. So you wouldn't say, well, these people are all in a lot more pain, so I want to put them in the treatment group because I feel bad for them. Because then, you're altering fundamentally the results based on the people you put in it. But in an observational study, it's fairly likely that the people in your treatment group have something in common, and the people in your control group have something in common. So in the smoking example, people who smoke generally have more in common than just smoking. There was a study a long time ago to prove this type of situation that showed that coffee was associated with lung cancer. And the reason is that, at least at that time, smokers drank a lot more coffee. Now it's kind of trendy and everybody does it, but back then that wasn't so much the case. And you could probably make a connection between smoking and alcohol, so that you could probably connect smoking with liver problems, and then maybe you could also show coffee is associated with liver problems, because people who smoke are more likely to drink and also more likely to drink coffee. But these are all things you can't control for in an observational study, but which you can control for in a design experiment. Within observational studies, we have cross-sectional studies. By the way, these notes may have things in them that aren't in your textbook for on-ramps, and I may have to check and make sure that everything from on-ramps is in my notes, but just in the case that you're at some point expected to know statistics, it's good for you to have some exposure to things generally taught in statistics. So cross-sectional studies are when you just take a group of people and you collect information for a kind of short period of time, maybe even just, in the instant. A case control study is when you ask people to look back in time, or you look at their existing records. So you not only look at them right now, but maybe their medical records or some sort of history that's related to what you're studying. A cohort study is a really, really strong study where you look at people over time, the same people. So you start looking at the people now, and then you continue to watch them over time. And that's harder to fund, obviously, but it's a really good study. A census is when you actually have the information about everyone in the entire population. So that's a pretty rare thing to get your hands on. Sampling methods. A frame is a list of all the individuals in a population. Random sampling is where you use chance to select the individuals. So the rule for it to be random is that every person has to have an equal chance of being selected. Simple random sampling goes a little bit farther and is the best. And with simple random sampling, every sample of the same size is just as likely to be chosen as any other. So if I were to take a list of all our third year learners, and I were to say, okay, I want to get 5 of them, then I could roll a 15-sided die, although I don't think that exists, but it would on an app on a phone, and start there, because I do have a list of all you guys, and then take the 15th person later, the 15th person after that, the 15th person after that, and so forth. Any person is just as likely to be selected as any other because that original roll of the die determines the people. But it is not a simple random sample because, for example, I couldn't get 2 of the Hughes triplets because I'm always going to skip 15 people and they're right after each other on the list. So that's the difference between random and simple random. A stratified sample is when you separate the population first into non-overlapping groups, and then you take a sample from each. So if I, instead of taking the list of you guys, were to go around and take 1 from each city, that would be a stratified sample. This is also how they do polls for Nielsen, for example, and Gallup, is they have areas of the population and they take someone out of each of them. A systematic sample is where you take the kth individual from the population, like the one before that I described for the random sampling. So it is a random sample, but it's a specific type of random sample. And then a cluster sample where you just take all the people from one subgroup. So if you took all the Dallas Mavericks and tried to extend that to the NBA, or if I just took everyone in Tampa, or I guess they're moved to Miami, all the people in Miami, and said that that was my sample for your grade. A convenient sample is one that you can just easily get, so there's really not randomness involved. So that could be standing outside Walmart and asking people as they go in, posting it on Facebook, something like that where it's just easy. So there's self-selected sample where the people decide whether or not to participate, which also happens when you're standing outside Walmart and posting on Facebook. And that ends up with a bias because the people who refuse to participate may have something in common besides just not wanting to participate. So it can confound your study. You should never ever have a very small sample. Very small samples are very skewed if you accidentally get someone who's an outlier. So biases in sampling, we have sampling bias, where our technique to choose the sample was bad. So if I were doing a sample from our group and I said, well, I want to know if people like anime, sci-fi. So I want to know if people are into fandoms. In that case, if I'd chosen Tampa, nope, Miami. Miami has got several people in it who are fans of those things. And so that would skew the results to look like a very large percentage were into fandoms. Non-response bias is when people who are selected to be in the sample but don't respond have different opinions. So if you, sometimes people call to do political polls, and the people who are most likely to respond are people who have very, very strong views about whatever the question is. So you end up with a bias based on that. Response bias is when the questions aren't really very good. They're written poorly in a way that's confusing, or maybe it's multiple choice answers and there are a lot of possibilities left out. So people really can ask questions in such a way that it leads people to agree with something they might not have if it was written otherwise, or disagree. So for the design of experiments, an experiment is a controlled study. I mentioned before you're trying to control for factors that might confound your results. So you want to make your treatment population and your control population look as similar as possible in every way except the explanatory variable that you are affecting. Blinding is where you don't tell the person if they're being treated or not. Without this, there's really no point in having a controlled experiment with a control group. So you don't tell them, you give them a pill or whatever it is. They've actually done these experiments with like surgery, so people have surgery that actually didn't do anything, which is a big ethical question. But anyway, blinding is where you don't tell them what's happening. Double blind is where you also don't tell whoever's evaluating them. So if you don't tell the person who you're treating, but you do tell the doctor who's testing their pain, then the doctor may subconsciously be affected also by knowledge of who's been treated. So as far as organizing qualitative data, we have frequency distributions, frequency tables. These can be created in RStudio. I'll wait until you've seen that done in RStudio, I think, before we start doing that. So I'll just show you. So here's an example. A phlebotomist draws the blood of a random sample of 50 patients and determines their blood types. So we want to create a frequency distribution. Frequency is just how many times did it occur. So if I wanted to make a frequency distribution of this, I would have type and frequency. So I have A, B, A, B, O. I'm actually, I think, a little bit beyond what I intended to do with this video, so I don't know how much farther I'll go with this. I do want it to have time to upload. So for A, I would go through and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. B, 1, 2, 3, 4, 5, 6, and AB, 1, 2, 3, 4, and then O, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. And then relative frequency means fraction of the total. So I'm just going to put this over here. Normally it would be a different table, but this is going to stand for relative frequency. And so I just figure out how many do I have here. So I have 50. So for relative frequency, I would either put 18 over 50, which I'd then simplify, or I'd put 0.36. So, or 36%. Any of those things is fine. So for B, I'd have the reduced fraction 3 over 25, or 0.12, or 12%. And for 4, 0.08, or 2 over 25, 22, 11 over 25, 0.44, any of those for relative frequency. So that's just where you take the frequency and divide by the sum of frequencies. I guess I'll do the bar graph and the Pareto chart for this, and then that's it. Okay, so a bar graph is not for numerical data unless you change it to be categorical somehow. So bar graph, you would have this bar for A, and then for B, they should not be touching. AB, O. So the highest I need to go is 22. Okay, so A needs to go to 18. And B needs to go to 6. AB to 4. And O to 22. Okay, so this is a bar graph. A Pareto chart is almost exactly the same. So all that I need to do is put it in descending order. So it needs to go O, A, B, A, B. So O, I hate it when I do that. A, B, A, B. So just in order that way, and now it's Pareto. Okay, so I'm gonna make this, I think, the end of the first video, and then I'll post at least one more tomorrow. Let's see where I am here.